Okay, properties of esters and amides. Hydrogen bonding of amides. So amides can form a complex network of intermolecular hydrogen bonds similar to that of carboxylic acids. It is this characteristic that causes the melting points of these substances to be relatively high. So we need to remember that amides have relatively high melting points, okay? Esters are unable to do this and thus have a lower boiling point and water solubility than comparable to carboxylic acid. So again, amides can form this complex network of hydrogen bonds that esters are unable to do. Esters can have hydrogen bonding, but it's going to be limited. And so if you take a look at this first picture here, you see there's hydrogen bonds occurring between amides. Now, remember that oxygen is more electronegative than carbon or hydrogen, and that's why we have these delta negative symbols on the oxygens. But if you remember, nitrogen is just one step back from oxygen in the periodic table, right? If you think of the second period, it goes carbon, nitrogen, oxygen, fluorine. So oxygen has an electronegativity of 3.5, but nitrogen is 3.0. And so that's why we have delta minus signs on the nitrogens as well. And they could have put one here, but they didn't put it here. So we have all these delta negatives. Now remember, the delta stands for what? It stands for partial, right? So that means that these nitrogens and oxygens, where I have the yellow highlighter, that means these all have a partial negative charge. And if they're partially negative charged, that means the hydrogens that they're attached to, like this one or this one here, they're going to be partially positive. Furthermore, the carbonyl carbons are going to be partially positive as well. And so when we represent a hydrogen bond, we represent it as a dashed line between a hydrogen and an oxygen, or between a hydrogen and a nitrogen sometimes. Now, the only ones they're showing here are between hydrogens and oxygens. And you can see they're showing a hydrogen bond here, again, between this delta positive and this delta minus. They're showing another hydrogen bond here between this delta positive and this delta minus. Now, if we look at the next one, okay, this is showing hydrogen bonding between water and an unsubstituted amide. So what it means by unsubstituted amide is it means this nitrogen doesn't have any carbon-based groups. It only has two hydrogens on it. So again, our nitrogens are going to have that partial negative charge, and there's only one nitrogen shown here. Our oxygens are also going to be partially negative, even in the water molecules, because oxygen is the second most electronegative element in the whole periodic table. And then the hydrogens are all going to be delta plus. The ones that are attached to hydrogens, the one on the carbonyl, like this, okay, these are all delta plus. So the hydrogen bonds, again, are shown as dashed lines between hydrogens that are delta positive and oxygens that are delta negative in neighboring molecules. So you see a hydrogen bond here between this carbonyl oxygen and this hydrogen in water. You see another hydrogen bond between the oxygen of this water molecule and the hydrogen that's attached to this nitrogen of our amide. And we see something similar here. Now, in this example, the last one in C, we have a di-substituted amide. What does that mean? It means on our nitrogen, we have two R groups, right? There's no hydrogens attached directly to the nitrogen. But we still have all of our delta minuses, right, on our nitrogen and our oxygen, right? Because these are the most electronegative elements in the periodic table. We still have all of our delta pluses for the same reasons that I explained before. And the hydrogen bonds, there's two of them that are shown here. One is between the oxygen of the carbonyl and a hydrogen of a water molecule, but there's another one shown between the disubstituted nitrogen and a hydrogen on a water molecule. And so you can see again, the amides can do this complex hydrogen bonding with water or between individual amides, as you see in the first example. Phenacetine. See a bottle of phenacetine with some caffeine in it over here. Anyhow, that doesn't look new, does it? Anyhow, it says here phenacetine is a pain reliever drug that was removed from the market in the 1970s because it can cause kidney damage, and it has the following structure. So it's very closely related to another famous compound, and that is acetaminophen or Tylenol. So if you knock off, so if you were to replace this group here with just a hydrogen, so if that was a hydrogen, it's kind of a ridiculous looking hydrogen, that would be Tylenol or acetaminophen. Anyhow, phenacetin nowadays, I think it's used to cut cocaine, but anyhow, that's neither here nor there. And so they're asking us to show how phenacetin can form hydrogen bonds with water molecules. Well, there's a number of ways you could answer this question, but if we draw a water molecule here, we could draw another water molecule here, like this. We could draw a water molecule here, like that, right? Because we know that the nitrogen is delta negative. We know this oxygen is delta negative. This oxygen is delta negative. All these oxygens are delta negative like this. But we know that this hydrogen in our water molecule is delta positive, as is this one, as is this one, like this. And so the hydrogen bond would be a dashed line here, or we could put one here, or we could put one here. Now, there's more hydrogen bonds that we could show, and I know the textbook probably has a different way of answering it, but this is perfectly fine to show our hydrogen bonds between water and the phenacetin molecule. And so this is the answer that they put in the textbook, which is similar to what I did. You see a hydrogen bond between water and this nitrogen. You see between the oxygen of water and the hydrogen that's attached to the nitrogen. I had this one drawn in and I had this one drawn in as well. So they just put one more than me. But again, they didn't specify the number of hydrogen bonds for us to show.